First, let's take a look at the first 4 sections of Chapter 1. We will start with the natural numbers. These are counting numbers like 1, 2, 3, 4, and so on. A long time ago, someone came up with the idea for 0 and created the whole numbers. The whole numbers are just 0, 1, 2, 3, 4, and so on. All but 2 whole numbers can be classified as either prime or composite. To be prime, a number must only be divisible by itself and 1. Since 1 is divisible by itself, which is 1, it is neither prime nor composite. As a rule, prime or composite numbers have to be greater than 1, so 0 and 1 are neither prime nor composite. On the other hand, 2 is divisible by itself and 1, which makes it the first prime number. Composite numbers are divisible by more numbers. For example, 4 is divisible by itself and 1 and the number 2. Being divisible by at least 3 numbers is what makes it composite. One fascinating thing about composite numbers is that you can rewrite them as a product of prime numbers. For example, 4 is equal to 2 times 2, where 2 is a prime number. Let's practice with some more composite numbers. Let's start with the number 24. We'll break this down using a factor tree, starting with 24 at the top and ending with only prime numbers at the bottom. First, find 2 factors of 24. For example, 3 times 8. We picked these 2 because 3 times 8 is 24. You can pick any 2 numbers that multiply to give you the number above it. 3 is prime, so it is done. 8, on the other hand, is composite, can still be broken up into more prime numbers. 8 is 4 times 2, where 2 is prime but 4 is not, as we saw earlier. 4 is 2 times 2. Now, we take everything at the bottom of our factor tree, our 3 2's, and our 3. What this means then is 24 is equal to 2 times 2 times 2 times 3, taking all of the prime numbers at the bottom of the factor tree. This is called prime factorization. Let's try this with another number, 132. Again, we find 2 factors that give us 132, say 11 and 12. 11 is prime, 12 can be broken down into 4 times 3, and 4 can be broken down into 2 times 2. Just as a general rule of thumb, when I go to write out the prime factorization, I'm going to start with my lowest prime numbers first, 2 times 2, and then increase from there to 3 times 11. So 132 is equal to 2 times 2 times 3 times 11. This is its prime factorization. Feel free to try this with a different combination at the beginning. For example, 132, instead of choosing 11 and 12 as factors, you could have chosen 44 and 3. The idea here is that no matter what factors you choose, you'll always end up with the same prime numbers at the end. Since this is an algebra class, one thing you'll have to become familiar with is the variable. Variables are anything that hold the place for a number when you don't know what the number is supposed to be. Like 4 plus 3 equals, I don't know, we'll call it x. Alright, this is just holding the place value for what 4 plus 3 equals. If I find out what 4 plus 3 equals, say I know it's 7, that means that variable x is equal to 7. Let's practice evaluating some variable expressions. Variable expressions are anything that contains a variable, say 8 times x. Anytime you have a number and a variable next to each other, it implies multiplication. So here 8 times x, or even y plus x. You can evaluate these by giving a number for the variable. So say in this case, I want x to equal 2. To evaluate this variable expression then, I just plug in the number 2 where the x was. This is now 8 times 2, or 16. for y plus x, I do the same thing. I have to be given a number for y and x to evaluate it. So say y is -1 and x is equal to 7. I then plug in these numbers, -1 plus 7, just where the corresponding variables were, add, and I get 6. So I've now evaluated this algebraic expression. Let's say I want to write a variable expression for this phrase, 6 less than a number. First I'm going to choose a variable to use for that unknown number. We'll call it x. And then I need to figure out, what does this mean, 6 less than a number? Well, say my number was 10. 6 less than 10 would be 4. So what I'm really doing is subtracting 6 from whatever that number is. So I have my expression x minus 6, and that is my variable expression for this phrase. Anytime you're asked some number less than something else, it's always that number subtracted from the second one. On the other hand, if I'm told a number less 7, again I want to choose a variable to represent my number. A number less 7 will say that number was 15. 15 less 7 would be 8. So really what I'm doing is subtracting 7 from that number. So I have y minus 7, and that is my variable expression. A little more complicated here, I have the product of 10 plus a number and 5. To write a variable expression for this, I need to know what a product is. A product is just multiplying two things, so the product of 10 plus a number is one piece, and 5 is the second piece. Those are the two things being multiplied together. So I have 10 plus a number, right, that number being a variable that I choose, and 5. Well, this whole thing is what is being multiplied by 5, so let's put this in parentheses times 5. Let's move along to fractions. Let's say I have something cut up into 12 equal pieces, and I take 10 of those pieces. I can represent that as a fraction as the 10 pieces I have out of the 12 pieces that the whole was cut into. This is called a fraction. Right? Always the numerator, or the piece on top, is what you have. On bottom, the denominator is what the whole was cut into. So I have 10 of 12 total pieces. In fractions, I want to write it in lowest terms, which means this same value written with smaller numbers. So for example, here 10 over 12, I can reduce this fraction by recognizing that this 10 is just 5 times 2, 12 is 6 times 2, noticing that each of them had a common factor of 2. I cancel out that common factor since 2 divided by 2 is 1, right? And 5/6 times 1 is 5/6. So 10/12 can be reduced to 5/6. There are no more common factors between the numerator and the denominator, so this is now the lowest terms. The easiest thing to do with fractions is to multiply them. Say 2/3 times 5/7. To multiply fractions, I just multiply straight across, numerator times numerator, and denominator times denominator, giving me my new fraction here. So 2/3 times 5/7, 10/21. Before I can declare this my final answer, I need to make sure that it cannot be reduced, that there are no common factors between 10 and 21, which indeed there are not, so this is my answer in the lowest terms. To divide fractions, let's say we have 4/5 divided by 6/8. When we divide, we rewrite our problem as a multiplication problem. Division of a fraction is the same as the multiplication of the reciprocal of that fraction. What that means is I take my 4/5 and I multiply it now by the reciprocal of 6/8, which is 8/6. The reciprocal is just flipping that fraction. So now I can multiply. Before I do, I can always check diagonally or within a fraction to see if there is a common factor I can cancel out before multiplying. Here I see that 4 and 6 have a common factor of 2, so I can reduce these two. 2 goes into 4 twice, 2 goes into 6 3 times. So now I can multiply here. 2 times 8, 16. 5 times 3, 15. And this is my answer in lowest terms. As long as I cancel out all of the common factors before multiplying, my answer will always be in lowest terms. I can double check here, and there are no common factors between 16 and 15. So indeed, it is in lowest terms. In order to add or subtract fractions, I need to have a common denominator. For example, 3/10 plus 5/10. Here, they both have a denominator of 10, which means the whole was cut up into 10 parts, so I'm comparing things of equal size. So I can add these two fractions, add the numerators. 3 plus 5 is 8, and 10 plus 10, no, don't do that. Right? That 10 is describing that the whole was cut up into 10 parts. So if I have 3 of those parts plus 5 of those parts, I still have 8 of those 10 parts. I never add the denominators. Now I can check my final answer to see if it is in lowest terms. It is not. There are common factors between 8 and 10, a common factor of 2, which I can cancel out. 2 goes into 8 4 times, into 10 5 times, so my fraction in lowest terms is 4/5, and that is my final answer. If I am subtracting fractions, say 2/3 minus 1/6, again, I still need that common denominator. If I do not have a common denominator to begin with, I need to create it. I need to look for the greatest common denominator, the number that both of these denominators can multiply into. In this case, 6. 6 goes into 6, and 3 can go into 6. If I multiply 3 by 2, that will give me the denominator 6 that I need. But in order to keep my fraction the same value, I need to multiply by 2 over 2, which we saw earlier is just 1, and I'm not changing the value of this fraction. I rewrite this now as 2 times 2 is 4, 3 times 2 is 6, and then now I subtract my 1/6. They both have a common denominator, so I can now take 4 minus 1, 3, and then keep that common denominator, 6. I now check to see if this is in lowest terms. It is not. There's a common factor of 3. I can reduce this now to 1/2. And that is my answer in lowest terms. Let's move on to exponents and orders of operation. In case you didn't know, repeated addition is just multiplication. Right? 2 plus 2 plus 2 is the same as 2 times 3. They both give you 6. Repeated multiplication, on the other hand, say 2 times 2 times 2, can be rewritten as 2 cubed with an exponent. This is 2 to the third power. In both cases, they are equal to 8. 2 cubed is just 2 times 2 times 2. This can even be done with fractions. Say 1/4 times 1/4 times 1/4. This is 1/4 cubed, or to the third power. What I can also do with this is raise each piece to the third power, the numerator to the third power and the denominator to the third power. 1 cubed is 1, and 4 cubed is 64. If I'm going to use exponents in an expression, I need to know the proper time to work them out, so I need to know the proper order of operations. I need to do things in parentheses first, so anything inside parentheses I work first, and I still follow these next 3 steps. Exponents and roots, so things like 2 cubed or the square root of 8, which we will get to later. Multiplication and division I need to do from left to right, so if I have 6 divided by 2 times 3, I do the 6 divided by 2 first and then multiply by 3. Addition and subtraction, doesn't really matter which order you do it. I could do 5 plus 7 minus 3 or 7 minus 3 plus 5. I'll get the same answer either way. You may have seen this problem floating around on the internet. Let's go ahead and take a look at it now, knowing the proper order of operations. So first thing I look for are parentheses, which there are none. Then I look for exponents or roots. There are none. Third, I look for multiplication. Here's multiplication. I do that first. So 5 times 0, 0. Now I do my addition and subtraction. 5 plus 5 plus 5 is 15, minus 5 is 10, plus 5 is 15, plus 5 is 20, minus 5, 15. So I have here 15 plus that 0, giving me 15 as my answer. So this is the correct way to do it using proper order of operations. Let's try a couple others. Let's say 5 plus 12 over 3. First I do my division here, 12 divided by 3, so I bring down my 5 plus 12 divided by 3, 4, 5 plus 4, 9. So I do division, then addition. Let's also try 4 plus 1 over 2 plus 8. This is a unique example because anytime you have problems written in a fraction, you want to do the numerator together first and the denominator together first. If there are no parentheses, you need to assume parentheses. So in this case we would work this out, 5 over 10, and then of course reduce our fraction 1/2. One last one here, let's take 10 minus 4 minus 3. I do what's in parentheses first, so I have 10 minus 4 minus 3 is 1. Then 10 minus 1 is 9. So that is now my final answer. Since we just talked about exponents, we should probably get a problem with exponents in it. Let's do 5 times 2 cubed minus 3 plus 2. So we have our parentheses first, 3 plus 2, so 5 times my 2 cubed minus 5. Next I do exponents, so I have 5 times 8 minus 5. Next multiplication, 40 minus 5, which is 35, and that is my final answer. Let's try writing the expression for a phrase again. Here 20 decreased by 2 times 3 squared. So we have 20 decreased by 2 times 3 squared. We'll go ahead and evaluate it and do our exponents first. So we have 20 minus 2 times 3 squared is 9. Do multiplication next. 20 minus 2 times 9 is 18. So 20 minus 18, 2. And that is our final answer. I mentioned back at the beginning natural numbers and whole numbers. Let's take a look at more of those. Alright, whole numbers again were 0, 1, 2, 3, so on and so forth. Integers, on the other hand, take the whole numbers and give their opposites. So counting below 0, 0, negative 1, negative 2, negative 3. Negative numbers come up when, say, you have a deficit or you're below the point of 0. For example, if you are below sea level, say I'm 3 feet below sea level, I am at negative 3 feet. These are our integers. Going beyond that, rational numbers are the ones that you can write as a fraction. So for example, 1/2 in between 0 and 1, or 1 and 1/5 here between 1 and 2. All of those rational numbers in between these integers are our next step of numbers. And then we have what are called irrational numbers, numbers that cannot be written as a fraction or an integer or anything else. For example, pi, or the square root of 2. These are numbers that can be written as a decimal, for example 3.14159, so on and so forth. Right? Pi is a decimal that goes on forever and never repeats. So it is irrational. All of these numbers combined, the integers, the rational numbers, the irrational numbers, are what are called the real numbers. So all of these together are the real numbers. Let's take a look at trying to organize some of these real numbers on a number line. I have here a number line. Let's say I wanted to plot the number 2. I find 2 on that number line and plot my point. I can plot any real number along this number line. Say for example 1.7. I can find that along here. It's going to be in between 1 and 2, closer to 2 here for 1.7. I can also do the opposites of these numbers. The opposite is just the negative of each of those numbers. So negative 2 I would plot here, and negative 1.7 again would be between negative 1 and negative 2, closer to 2 here. Let's also go ahead and plot, say, 1/2. Again, 1/2 is going to be right in between 0 and 1. Its opposite, a negative 1/2, will be in between 0 and negative 1. If we want to plot, say, an irrational number, for example, pi, remember, is about 3.14. It's going to be just past 3, and negative pi is going to be in the same place over here, just past negative 3. So these then are all of my numbers. Going from least to greatest, I have negative pi, negative 2, negative 1.7, negative 1/2, positive 1/2, 1.7, 2, and pi. You'll see that every positive number is always greater than a negative number. Here we notice negative 1.7 is greater than negative 2. Also, negative 2 here is greater than negative pi, where on the positive side, pi is greater than 2. You may have noticed that to make 2 opposite, I put a negative in front of it. Well, I can also find the opposite of negative 2 by putting a negative in front of that. The negative 2, right, the opposite of negative 2 is a positive 2. So what we see here is that double negative is the same as a positive. This is only when the negative signs are right next to each other. So don't get confused if I have, say, negative 3 minus 2. This is not a double negative. This is negative 3 minus 2. And if we follow that along the number line, right, if I'm starting here at negative 3, I'm going to go now to the left 2 from that, negative 4, negative 5. So this is minus 5. These numbers, 2 and negative 2, are what are called additive inverses, which means if I take 2 minus 2, or 2 plus its additive inverse, negative 2, I get 0. Alright, so I promised we'd get to square roots, so let's go ahead and do that. Squaring a number, say 6 squared is 36. The square root of 36 is asking what number times itself gives me that 36. So the square root of 36 is 6. More square roots are, say, the square root of 81 is 9, since 9 squared gives me 81. The square root of 100 is 10. The square root of 9 is 3. And the square root of 4 is 2. You'll see here 2 squared is 4, 3 squared is 9, 10 squared is 100, and 9 squared is 81. These are square roots. These are special cases because these are perfect squares. Whereas, say, the square root of 8, there is no whole number that I can square that will give me 8. This gives me 2.8284, so on and so forth. Okay, this number will go on forever and it will not repeat, making it an irrational number. Another cool thing you can do with numbers is find the absolute value. So for example, the absolute value of negative 8 is asking myself on that number line here at negative 8, how far is that to 0? Well, if I'm counting here, that's going to be 8 spaces. So negative 8, the absolute value is 8. Anytime you take the absolute value of something, say negative 3, it always spits out a positive number. Also, a positive absolute value, so absolute value of positive 2, again here it's asking how far is it to 2, well it's just 2. So absolute values always spit out a positive number. The way you can get around that by getting a negative number is putting a negative in front of your absolute value. So this is asking for the opposite of the absolute value of negative 7, where the absolute value of negative 7 is 7, but it wants the opposite of that, so negative 7. The last thing we need to be able to do is make sure we can classify and organize all of our numbers. So for example, the number 2/3, also written as 0.6 repeating, where 6 goes on forever. Right? This is a rational number. The number -2 is an integer. It can also be written as a rational number, -2 over 1, but it cannot be a whole number since it is negative. 2, on the other hand, is an integer. It's also a rational number, and it's a whole number because it is positive, and it's a natural number, right, because it is not 0. What about the number pi? Well, pi is 3.14 going on forever, but never repeating, so it is irrational. It cannot be a rational number. Irrational numbers have nothing to do with these, whereas that natural number, say 3 or 2, can also be a whole number, an integer, and a rational number. Irrational, on the other hand, those numbers are completely separate. Another example of irrational, the square root of 2, or as we saw, the square root of 8. Square roots of non-perfect squares will give you irrational numbers. Square roots of perfect squares, say 9 for example, that gives you 3, which is our natural number, whole number, integer, and rational number. If we're going to throw these all on a number line, we can put here 0, just to know where to go from there. -2 would be to the left of that. 2 would be on the opposite side, and the positive side. 2/3, right, that's going to be less than 1, right, but greater than 0. Here's our 2/3. 3 will be above our 2. The square root of 8 we saw was 2.8 something, so it's going to be between 2 and 3. So we have our square root of 8. And then square root of 2 is going to be right about here, right around 1.4 is the square root of 2. And then pi will be a little greater than 3, right around 3.14. Here's our pi. So that is the correct order for all of our real numbers. That's going to do it for Chapter 1, Sections 1 through 4. I hope you enjoyed. Make sure you go back and rewatch anything that you were confused on. Feel free to pause, take notes, whatever. And then go ahead and check Blackboard for the rest of our assignments, homeworks, quizzes. You can also find the discussion board, so if there are any questions you had from the video that could not be answered here, go ahead and ask those in the discussion board. Hope you enjoy. I'll see you later for the next 4 sections of Chapter 1.